Okay, so now I'm going to do this other problem. So this is another way we can use the Clausius-Clapeyron equation. We can use it to calculate we can use it to predict what a boiling point will be at a different pressure. So in Breckenridge, Colorado, the typical atmospheric pressure is 520 point torr. What is the boiling point of water in Breckenridge? So now, for this problem, I'm going to use the other version of the Clausius-Clapeyron equation because I want to solve for a temperature. Okay? So I'm going to use this version. I'm going to say natural log of P1 divided by P2 equals delta H of vape divided by R times 1 over T2 minus 1 over T1. And I can actually use all of these same, more or less, I can use all these same parameters because it's water. So, but I'm going to define this in a way that makes it easier to solve. So I'm going to say T2 is the number that I want. What's the boiling point? At 520 torr. So if P2 is what I don't know, then P2 has to be 520 torr. I'm going to pick the same boiling point situation that I picked last time. I'm going to call T1 373 Kelvin and P2 760 torr. Okay? And I know that my delta H is the same and my R is the same. And you'll see why I picked these numbers for 1 and 2, because it's going to make it easier to solve. Okay? And so I'm also going to just do a little bit of algebra to get started. I'm going to say natural log of P1 divided by P2 divided by delta H of vape divided by R. So I'm just moving that whole thing over to this side, equals 1 over T2, okay, plus 1 over T1. So basically, I tried to isolate T2 as best as I can because that's what I'm calculating. And it might be tempting for you to further this algebra and just say flip it 1 over. But the way that I like to do this now is calculate all of the stuff that's on the left, and then I'll flip my final answer at the end. Okay? So let's plug some stuff in. So let's see here. So 1 over T1 is 1 divided by 373 plus the natural log of, so P, oops, that looks like a 2 that I wrote there, doesn't it? That's a 1. So natural log of 760 divided by 520, all divided by 4.07 times 10 to the 4th joule per mole, all divided by 8.314 joule per mole. Okay, so I got to calculate all of this stuff. So let's do that. So we already know from up here that 1 divided by 373 is 0.002681 plus. And let's see, the natural log of 760 divided by 520. So first I'll do 760 divided by 520 equals. Now I'm going to say natural log. So that gives me 0.379, let's go one more digit, 5, divided by 4.07 times 10 to the 4th divided by 8.314. And actually we did that already up here too, right? Up here, this 4.07 times 10 to the 4th divided by 8.314 was equal to 4895.4. So let's write that down there. 4895.4. And again, I've dropped the units to make this easier, but the units are going to be Kelvin, right, when it spits this out. Okay. So let's see. Let's keep that going. So now let's say 0.3795 divided by 4895.4 equals, and then now plus 0.002681 equals. So that so this whole chunk is 0.00275. Let's call it 9, and that equals 1 over T2. Right? So on my calculator right here, I can find the 1 over x button. There it is. and I'm just going to push it. Beautiful. That gives me 362 Kelvin. Let's just keep it at that. 362 Kelvin. And if you're curious what that is in terms of Celsius, so minus 273, so that's 89 degrees, 89.5 degrees. So as I told you earlier, when you're way up there in the mountains, liquids boil at a lower temperature. And in this case, when the atmospheric pressure is 520, that's a significant drop in the boiling point due to the reduced pressure. Okay? So